That's what I was working on. I'll just pick it up.
All right, so now we've had most of them trickle in. First things first, guys. If you don't have a laptop that you can and would be interested in installing Altium on, which is a PCB design software, send me a message in Canvas, because I would like to teach this in Altium, but we don't have it on the lab. Altium is free to students, you're just going to download it, but not in our labs. If not everyone has it, I'll just go learn Eagle or something terrible that's beginning, because I think everyone kind of wants. Question?
How big is it? Is it like 20 gig?
I haven't installed it in a long time.
The real deal is huge.
Yeah.
What?
I said, give me 5 minutes.
Okay, 5 minutes, he's gonna have it. For the free version.
I mean, I can do something else that isn't Altium. I just want, because Altium is
Awesome.
the most professional, like the most used professional program in the world. And it's growing. So that's the one that I would prefer to use, because it's not, I wouldn't just be teaching you concepts. I'd be able to teach you the actual tool that you will more than likely end up using at some point in your career. However, since I don't have it on the labs, I want to make sure that whatever I teach is everyone, or if people are comfortable like sitting next to someone and doing it, I can do it that way. You know, I just want like a count of the number of people that can't do it. So just send me a Canvas. I don't want to like embarrass anyone. So don't worry if you can't do it. Just send me a message and I'll see if I can pull off Altium, because it is a very good program, actually, surprisingly good for engineering software. It does more than PCB work, but that is what we will use it for. Yes. Yeah. So this would be kind of the introductory Altium stuff.
7 gig? Okay.
Yeah. So you can also do like high-speed signal analysis, data integrity, things like that. But we won't get that far, I don't think, because I'm just going to do a lecture or two on it. And I'll do it in the context of what are good design practices for this type of sensor circuit, right? So what I'm working up to here to now, because one of the hardest things to do is layouts for precision amplifiers and ADCs. So last time we talked about signal conditioning for audio amplifiers, and this time I'm going to go on to more signal conditioning circuits. These ones are a little bit more interesting to me. These are some of my favorite circuits actually to talk about. It took me a bit of effort to translate this from the integrated circuit design perspective of these circuits into kind of the instrumentation side. So what we're talking about today is really going to be, how do we deal with very low frequency signals in precision amplifiers, and what kind of concerns do we have, right? Because a lot of sensors are very low frequency, right? Even DC is a lot of what we've talked about. And there are special considerations that we need to take, special things we need to take into consideration in order to design amplifiers for it. And some of the amplifiers that are best suited for it scare people off, because either they don't know they exist, which means they don't know what they are. So when they go out and search for them and go, oh, I don't know what that is, or they don't know how to use them. And so they're like, oh, there's all these problems, so I'm going to avoid them. So I'm going to talk about some of these precision amplifiers and some of the considerations and why you would use them. And that's what we'll do today. So when we're talking low frequency measurements, right? And I've talked about this a while ago, but we'll bring it back in. If you look at the characteristic of like noise versus frequency, right? In an amplifier, it looks something like this, where you kind of have your wideband thermal noise, right? That kind of just is intrinsic to the device. And then up here, we have this 1/f noise, which we call peak noise, right? In amplifier design, there's not much we can do about this 1/f noise, except for to make the transistors bigger. That's pretty much where it comes, or we can dump more current into it. You know, there's little things we can do, but as like not IC designers, there's nothing we can do about it, right? So we kind of have to live with this 1/f noise, and it's not necessarily 1/f. It can be like 1/f squared, or you know, it can have an exponential here, but we just typically call it 1/f noise. It has some characteristic to it, and it gets problematic because the lower the frequency, the worse the noise gets, right? So these amplifiers that we want, when we start measuring in this low frequency range, can run into noise issues. So, and this we call the 1/f corner frequency, right? Because that's where it where the intersection of the 1/f noise becomes dominated by the thermal noise, right? So the real curve looks something like this, because in this region is really an addition of the thermal noise plus the pink noise, right? So, okay. So what we have then is like way down here, right? If we imagine it goes all the way to 0, is your DC offset, right? Which we're going to call VOS. Now this offset is also subject to something called drift. And this drift has really two major components to it, right? It's thermal, like if the temperature changes, but also as devices age, they actually change. Right? So the offsets change over time, which can be problematic. Let's talk about offset real quick, right? So I've mentioned it before. We typically want an ideal amplifier to have no offset. So if we were to take an amplifier and connect its inputs to ground like so, we would expect to have 0 volts at the output, right? But we don't, right? We could hook up this kind of thing and go measure the output. But if we use the term precision amplifier, that usually means that this VOS that ends up here is going to be somewhere in the range of 10 millivolts, right? If it's not less than 10 millivolts, we're hard pressed to call it precision amplifier. But 10 millivolts is a lot potentially on our amplifier, right? And the way we usually indicate offset voltage is input referred, right? We like to talk about input referred. So we're going to put like a little voltage source here and say that we're going to have some noise source, not really noise, right? Because it's DC, some DC component that's going to create an offset. And it's not hard to imagine a situation where 10 millivolts or even 1 millivolt is too much, right? So one of the examples that I like to use is, let's imagine that we want to design a system that's going to measure the concentration of gas in a chamber, okay? So we're going to have some sort of IR frequency. Now what's nice, and you may or may not realize, is that if I look at the spectrum of light, and I'm going to use air as the gas. So say we have like mostly a vacuum and I want to measure how much air is in a chamber. Well, if we're using light to this measurement, right, there actually light has some sort of impedance versus light, right? It is hard to pass through things, which means if I point a laser across a long distance, eventually it will fade, right? Well, light is kind of interesting because it has this characteristic. It does a bunch of stuff in here where this is the wavelength, and this is what we'll call opacity, okay? So somewhere in this region, this divot is the visible spectrum, which I'm just going to write vis. Okay, the visible spectrum falls somewhere in this region, which is centered about, the high end of visible spectrum falls down about here and is about 1 micrometer, okay? Which, right, we can translate wavelength into frequency if we wanted to. And it's kind of right at this, almost the 3 dB point here. Which falls down somewhere around 500 or 0.5, I guess as well, do 500 micron. Somewhere in that region's this, right? So as far as light goes, the visible spectrum is not very wide, okay? Well, anyways, if we want light to pass through, it turns out the visible spectrum is a really good thing to do. Right? But if we go to lower frequencies, it becomes more opaque, and there are certain peaks down here at higher frequencies where it's actually, light is actually fairly opaque. And we can take advantage of that if we're trying to measure the concentration. But despite that, it doesn't block a whole lot, right? It doesn't block a lot of that light. And so what we want to do in the case of the laser sensor for measuring concentration is just measure how opaque something is. But this is a DC measurement, essentially, right? Is if we wanted to build a simple circuit that could do this type of measurement, we could take something like a photodiode. This is poorly drawn, sorry. Like so, right? This is a really simple circuit that the more light there is, the more conductive it becomes, okay? Well, the issue here is that if I'm trying to amplify this signal and I have any sort of offset in the amplifier, because I'm going to want to null out whatever the offset is because I'm going to have very small changes here. So I'm going to try and bias this guy right somewhere in a linear region so that I actually get response to it. And then we're going to amplify that. But the change in the signal is going to be very small compared to the signal itself, right? The bias. There's just no way around that. So we don't want to add any offset of our amplifier, especially something that's going to drift over time that we're going to go ahead and give someone like as a product, right? Because if it's going to change over time and that change is bigger than the signal that we're trying to measure, we have a problem, okay? So one of the ways that you can do it, and this doesn't solve the over time drift, is called trimming. Right. So if you go and look at a lot of amplifiers, they have something that are like called trim pins or something. Where's an eraser? I guess I'm going to walk all the way over. So we might have an amplifier that's something like an LT1097. This is a real amplifier that has real trim pins. It has inputs, its trim pins. We're going to draw coming out. They're pins like 1 and pin 8 or something like that. We stick a pot between them. We stick this into VCC. Has power rails obviously as well, right? And I can spin this little potentiometer back and forth, and it will change the, in the case of the 1097, as I can actually add plus or minus 600 microvolts of input referred offset, which is pretty cool, right? So I can start reducing some of that offset. However, this doesn't help me if the temperature changes or aging of the device, right? So this kind of trim pot is what we'll call it most of the time, is very useful, especially if you're like prototyping on board, right? Because then you can kind of dial it in and get rid of your offset as a one-time measurement. Now you can very easily imagine kind of a feedback system that measures what the offset is and corrects for it, and that works. That is again susceptible to whatever devices are providing that feedback have drift, right? So if you have that drift, then we have a problem. So we kind of need to look at how can we design an amplifier that is independent of offset and drift, right? That's one of our big challenges. In other words, how can we do, what amplifiers do we have that we can use to avoid low frequency problems like offset, drift, and peak noise? That's how I'll phrase it. Now, I'm not going to ask you guys to design these, right? This isn't an IC design course, but what I want to focus on is how these types of circuits function so that you can comfortably use them if they come around, and at least you know they exist so that they're an option. So we could refer to that first one as static offset correction, right? Because you do it once and it is what it is. But now I want to move on to dynamic offset correction, DOC, if we're going to abbreviate it. I don't know that I will in language, but I do if I'm writing it. And there are two main ways that we would think about dynamic offset correction. And the first one corresponds to that guy, which is where we want to measure the offset and subtract it, right? In this case, we manually measure it and manually correct it. Adding a feedback loop there could measure it and then correct it, right? That's basically what we're going to do, is measure and correct. The other offset correction method that's dynamic is we can try and push the offset around, make it somewhere that the signal isn't, right? We can either move the signal or we can move the offset and make it so that they don't interact. The first method that we'll talk about, which is measuring it and doing something with it, is called auto zeroing. And the second method is called chopping. Now, these two amplifier architectures are actually fairly new. If you go back and look for some like the earliest, I guess almost like tutorials, like application notes, date only like 2007 or something is about their age. Did I bring my drink in here? I'm going to run out of voice. All right, I'll run out of voice today. That's fine. So auto zeroing is measuring correct. That measuring part is actually discrete. Okay, so it's actually going to step in, measure it, and then correct. So it's actually a discrete time method. I'm going to reference auto zero as AZ from here on. And the benefits to both auto zero and chopping are kind of the same as the trimming, right? They're going to reduce DC offset, drift, and pink noise. Okay. There is a bit of a mistake that if you go read the literature, it will often say eliminate. They don't eliminate, right? Nothing is that ideal. It removes or it reduces. Okay? It's going to be good. So what we're going to do is that, of course, is talk about the costs. What are the cost trade-offs of each of these? In general, you're going to have a bandwidth reduction. We have to spend something in order to make this work. So in general, we're going to lose some bandwidth. We're going to have to increase complexity, and we're going to have to deal with aliasing, right? Especially in the auto zero case, because I said it's a discrete correction, so it's going to have aliasing. Anything that you sample is going to have aliasing. So the zero drift is another word that you hear refers to it. Zero drift is kind of this overarching idea that encompasses both of them. Okay, these are zero drift amplifiers because they remove the drift. Okay, they have. I talked about the cost perks in like explicitly or DC precision, low offset, low drift can potentially eliminate 1/f noise. So that's actually one time where we can say it can eliminate something. It doesn't just reduce it, it can eliminate it. And it turns out as a perk, because CMRR and PSR, common mode noise and power supply noise are often low frequency stuff, it actually improves both PSRR and CMRR, which is kind of cool side effect. So if we go and look at auto zero first, okay. Auto zeroing is the easier one to describe, so that's where I'm going to start. The offset. Okay. It requires switches to make this work, right? And the switches are where the sampling concept comes from. And let's talk about this in two phases, where there's going to be an auto zero phase, which is where we're going to go ahead and sample what is our offset, right? And we do that by closing switch 1. So we're going to call this phase 1 and closing switch 2, feed 2, okay? If we close both of those, right, we have a circuit where the input is tied to ground. So the thing that it's measuring is just this offset voltage, right? And there's really a combination of these two, but I can put it both onto one terminal just fine. And S2, sorry, phi 1. Both of these are phi 1. This is going to be phase 2, okay? So this is the AZ phase. This is going to be, what do they call it? The amplification phase. All right. So closed switches 1 and 2. We put the offset voltage through the amplifier. It feeds that back around, right? It's nothing but that offset and throws it onto the auto zero and capacitor, right? Then when we release them in the next phase, switches 2 and 1 open, we throw V in into S3, and now we have the offset stored onto CAZ, the capacitor, and the offset's still there, it's the same, into the positive node, and they subtract out. Right now, you'll notice that this particular architecture is kind of simplifies because I've broken in the amplification phase, I've broken the feedback loop. Right. So you have to go look at a more complicated architecture if you're going to talk about how they actually implement these in a circuit. Now, as I mentioned, you're not going to design this. You're going to go buy something that has this in it. But to do so, if you're going to choose that as your amplifier, we need to understand essentially what we're doing, at least conceptually. Right. So that's the basic idea of how they work is let's just go ahead, step 1, measurement, step 2, amplify and subtract. But this 2-phase thing is why it is discrete time, okay? It turns out that this amplification isn't perfect. It doesn't exactly reduce your offset voltage, but it does reduce it proportional to the gain of the amplifier. So the more gain the amplifier has, the better reduction it does. And this is the term that we call this, sorry, is the V res, which is residual, the residual offset voltage.
Is it the open loop gain of the op-amp?
Yeah, in this case, yes. But it can be the closed loop in the case of closed relay. So this would be like if we were trying to build a comparator with no DC offset, essentially, right? Which is a real application for this. It turns out that using auto zero in comparators is really pretty great, whereas using them in the choppers, which I'll talk about later, is really bad, okay? There are, of course, actually some problems with this, and I always like to talk about the non-idealities of any circuit so that you guys at least start getting familiar with them. So when you design a circuit, you're not terrible like some of the coworkers I've had in the past that are just oblivious to the realities of circuit design. So, has anyone heard of charge injection? Little bit. All right, that's kind of what I figured. I never heard of it when I was in my undergrad either, so it's helpful to talk about. So basically, what happens is when we're using a CMOS device as a switch, which is really ideal, right? Because CMOSs are very small, and as long as we can control the voltage is kind of on or off, we can actually make them fairly low impedance. And so they have kind of these desirable characteristics. However, it turns out that when you're using them as on, they're pretty good, right? Because you're using a voltage to control where the electrons are going. When you turn it off, you lose control of what it's doing. You're just like, hey, stop doing that. And what happens is that the capacitance of those devices have stored up a bunch of charge that it then just kind of dumps. And you have no control over which direction they go. Those electrons will out both sides of it and cause what we call charge injection. So why is that a problem? Well, let's go look specifically at S2, right? It opens. So we've stored the charge on capacitant, the CAZ that corresponds to the offset voltage. This opens, it throws out a bunch of electrons that then get stored, at least some of, on this capacitor, and now we have an error, right? We haven't measured we measured exactly our VOS, but we've now ruined it with this charge injection. So you can go and actually build really complicated circuits that like measure the amount of charge injection and subtract it out off of, right? We can start getting rid of some of these issues by just spending money or complexity, right? But in general, that is a real issue. And anytime you're dealing in the analog world and you're using a multiplexer, you're going to have this issue, right? So this is something that people fail to recognize in precision cases is they don't account for the charge injection of any of your switches. All of your switches that you ever use have this, unless they're like mechanical relays, but they have their own issues. For just a reference number, I just pulled some random reference numbers that if you're using like a 700 nanometer process, which is really old, okay, by this point, this is like the This number comes from like a 2007 paper, so it's old. This is the early days. So 700 nanometers, and let's see, sorry, 2.5 volts that I'm stepping over this. That's my change that I'm trying to record. And I'm just using a really small 10 picofarad capacitor. My residual offset's gonna be like 250 microvolts, which is potentially substantial, right? Depending on our application. Fortunately, as the technology gets better, the smaller devices have less charge that they can store, so the charge injectors become less and less of an issue. Again, there's a trade-off because the smaller they make the device, the higher the impedance gets, and that itself has some issues. That issue, right? If there's impedance on it, we treat it like it's thermal noise. That thermal noise then applies to the input, and we've ruined our signal just a little bit. This thermal noise here gets stored on that capacitor as well, which is really just kind of a snapshot of the total integrated noise over the bandwidth of interest, right? That's kind of the issue is the more thermal noise we have, the more it gets stored on this capacitor. And really the longer that phase is in that we're measuring, the more integrated noise that I get. So kind of switching fast can kind of help this issue a little bit. But we also have the bigger capacitor as help because there's kind of, anytime you have like capacitive feedback circuits, you basically just go the noise is equal, the noise power is really KT on C. Right, you guys seen this relationship before? Great, right? So that's what it is. So we make a bigger capacitor, we get less noise, but it slows the circuit down. Right, pretty intuitive. The downside is if you are an IC designer, big capacitors are huge. In an integrated circuit, capacitors are very big. So we don't like using big capacitors. So that's why the 10 picofarad makes sense, right? That's a fairly small capacitor you might actually use in an integrated circuit. The last issue is, I mentioned that this is a sampled system, right? And there's aliasing issues. So let's go and use like a simple example where the bandwidth of the amplifier needs to be kind of big compared to your actual region of interest, right? So that you can actually settle in time. That's one of the downside to auto zeroing is I need a bigger bandwidth. So if we have, I'm going to just do the single sideband just because it's a little bit easier. And my bandwidth of interest that I'm actually measuring, or my sample rate is another way of saying that, my sample rate of my auto zeroing is, I'm going to call this FS. And I'm going to go out to 2FS. This makes it really easy of my bandwidth for my amplifier so that I can actually settle out these changes. And then my noise, let's say it looks something like this. This is like my thermal noise. It's fairly flat. This is going to really have some roll off or something, but let's just go ahead and treat it like a truly sampled system. And what it's basically going to do is take all of the excess noise because I'm undersampling, right? So when I undersample something, it just takes whatever is higher frequency and thinks that it's a lower frequency than it is. You know this from signals, right? At least have a little bit of DSP in that class, I think. Is anyone not familiar with that idea? Okay, I guess we're doing okay. You guys are just quiet. So it's undersampling all of this because the FS is smaller than 2FS, and you end up with a nice big pile. Well, right, it's mirrored, but I don't need to do that, of noise that's in band. So this does add noise to the system. Again, trade-offs. Nothing is perfect. Okay. So what does this actually look like kind of in a practical sense is, and I'll try and use another color and just overlay it. If we say something like, well, the amplifier noise initially looks something like, don't correlate the red and the blue just yet. So we look something like this, where this is our pink noise, this is our thermal noise. If we auto zero, it tends to shape it down like that. So we get this region that we've kind of exchanged a bunch of noise here for a little bit noise there, right? Which is kind of nice. So now, if this is our region of interest, we've done really good. You can kind of go ahead and estimate the noise factor that you have. I was going to have you kind of go through to do that, but I don't think so, because like the data sheets will usually kind of tell you what that is. The reduction, I don't know, you can do like 10 times better in this kind of crossover region there, or the amount of noise, like the total integrated noise over that bandwidth of interest. You can do like 3 to 10x improvements, which is pretty cool. There's the other issue that I will point out explicitly is that you have downtime in this amplifier, right? Anytime that you're sampling the offset, your amplifier doesn't function, right? It is not amplifying, we've lost that signal. So it is not continuously able to measure. It turns out that the way that you simplify, like fix that problem is really easy, in that you take 2 amplifiers that are both auto zeroed, put them in parallel, they sample at different times, they have switches at the output, now it's continuous. It turns out that if they have the same period essentially between those, that actually introduces more noise. And there's this really cool solution to that, right? Because if I have 2 in parallel, it's going to make more noise. It turns out that if you make the 2 non-periodic with each other, so, or even just random, then they lose correlation and the noise is non-correlated and it subtracts itself out as well. Which is kind of cool.
Do you have to worry about chaos theory with that?
I don't have an answer for that one, because I will be honest, I've done much less work with the auto zeros than I have with the choppers, but this is an easier introduction to the idea. Okay, one of the cooler ones that I really like that we can kind of build on from here is this is where we start making it make a little bit more sense, right? And let's build it beyond the comparator, right? Because the first example was really just a comparator. Minus differential. Just grab it, that's easier to deal with. And then take a second amplifier that is a differential amplifier. This guy goes over here, this guy goes over here. And plus minus. So this is a little bit more complicated, where we're going to have a main amplifier. We're going to call him M because he's a main amplifier. He is a normal amplifier. There is nothing special about him whatsoever. He has some gain, bandwidth, he has peak noise, he has all of that. Then we're going to take an AZ amplifier in a parallel path. Then this guy is going to be designed to subtract out. Basically, we're going to add in a negative signal into a different path, right? This is kind of like a summing amplifier that we've talked before, where we're going to actually go look at the offset voltage that results from the inverting input and the non-inverting input. So we're going to compare those two, just a low frequency. This guy's going to be a fairly low frequency amplifier. Go measure those two, get and look at what that is and not contribute any of its own. Right, so he's going to actually cancel out all of his own because he's auto zeroing it. And I should say all, but I don't mean all, right? And then tell this guy what his is and subtract it out there. That's all he's doing.
On those op amps, is that connection between them to the offset part, or is that the positive and negative rails?
This is the offset part. I haven't drawn any of the rails.
Oh, you wouldn't apply to it.
Yeah. This dual path kind of thing, right? We kind of talked about before. This concept isn't entirely new. There's something similar that we did in the audio amplifiers, right? Where we use different amplifiers for different bandwidths. This is a dual path amplifier for a different purpose. It's just we want one that can do very good job of removing its offset.
Is this chopping or no?
This is not yet chopping. This is just what they reference as offset stabilization. It actually turns out you can use a chopper amplifier instead of the auto zero here, and it's very similar. It's just that, like, you can imagine, actually, maybe I have a better circuit that I can even compare it to. Let's see how much I have to redraw to make this one make a little more sense. So let's turn this explicitly into an auto zero. Instead of having like this implied auto zero, let's go ahead and make an explicit auto zero, where we're going to have it go ahead and have these switches. S2, he's going to switch from a differential to a single-ended. There we go. Once again, this input is not the power rail. This is kind of a summing node that we're going to add something to an offset specifically, right? This is like one of those trim nodes, but instead of sliding a potentiostat across two of them to adjust, we're just going to put a voltage in that we want to subtract, right? It's just like a third node. So what this guy does is the same thing. In one phase, he connects those two. He goes and samples the offset. He then goes and dumps that charge in the storage that stores both his and the measured. Okay, so he adds up both of their offsets here, and then goes and pushes that back onto, this is now CAZ, this is our auto zero cap. He dumps the charge on there, this guy subtracts it out. The nice thing here is, as long as this isn't pulling very much current, this guy doesn't even have to be periodic. He just has to go and monitor, like, you could have even another circuit that feeds back around and be like, oh, you've drifted. Go take a sample and update the value on CAZ. Right. So this can be a non-periodic disruption. Because anytime I throw these switches, I'm going to get charge injection that gets thrown into here, right? Has a little spike in it and kind of ruin the measurements a little bit. It's not too bad because it's not a highly precise measurement as much. And it's high impedance, so it deals a little bit better. But still, throwing those switches is not ideal, but we can take a moment, latch it down, take a sample, do it, disconnect, subtract. However often we feel like we need to do this update. And in some systems, it's really slow. Sometimes it's like once a second or something, which is really slow for an electrical system. The other cool one that you can do is you can take this auto zero and realize that, well, it's discrete. It's already discrete. So I can skip the whole analog side of things and I'll keep this nice and abstract. So let's look at this as a system level. Right, I have some amplifier that's not choppered or auto zeroed. It's just a regular old-fashioned amplifier. It's measuring the V in, it amplifies it up, it stores it in the AC and goes into the microcontroller. Well, intermittently, I can go pull out, connect it to ground instead of the signal, record that in my ADC, save that in a register in like the microcontroller, FPGA, whatever we're using, and then subtract that out. Right, I can do all of this auto zeroing. So this is one that you can actually design yourself because you don't need a special amplifier. You just need a control register, right? That this microcontroller goes back and tells this switch when to sample. How often do I need to measure this offset that I'm now going to correct? right? And the nice thing is that if this ADC has its own offset, it's also measuring, you can also measure that, right? It's actually going to subtract its own problems. Pretty useful, pretty handy. It actually does apply to something that you could go build, and maybe I'll find an excuse. I don't know that I'll have enough time, but it would be kind of fun to do that. So this one is kind of what they would call, let me, I want to just see if I want to go into this. Anyways, you can kind of just switch back and forth fairly fast. The benefit there is the faster you go. So if you do this slowly, all it does is offset. The faster you go, the better it suppresses pink noise. So this actually does help with pink noise suppression. We'll never eliminate it, but it is proportional to the rate at which you switch back and forth, the pink noise suppression. So that's kind of cool. If I had good enough equipment in the lab, I would totally want to do that one. I just don't think it's quite there unless I could find a really noisy amplifier in order, because you could build this, right? We could go get like a Arduino or something stupid and just tell a switch to it back and forth and see if we can subtract out the pink noise. So in general, in summary, for these auto zeroings, you kind of end up with offsets pretty easily in the 1 to 10 microvolt range instead of like the 1 to 10 millivolt range for kind of traditional amplifiers. So if you need very low, they're essentially immune to drift over time. It won't have any effect on them. They're very resistant to that. If you do the parallel topography, this has another benefit in that we don't lose any bandwidth at all here. We lose like 1 moment in time every time we sample that the data is a little bit noisier. We lose no bandwidth. It does add noise. These guys, the resistance of these do actually pile a little bit noise on. And you have that noise aliasing problem still that goes through here, but it's a smaller amount, right? Because it's just proportional to the offset instead of the main signal. And auto zeroing is really the choice that you're going to go for if you're already using a sampled system, right? Because if you're sampling periodic in time and you're going to go ahead and sample this, we don't really care that we have these intermittent disruptions because we just won't sample during that period of time, right? We can just avoid it. So this is a great solution if you're sampling shortly after it. Yeah. So let's switch over to the chopping mode, which chopping, I love choppers. They're a lot of fun to design. If you're ever like doing integrated circuit, if you want to do your PhD like a crazy person, and you do an IC design, I recommend looking into choppers because they're just fun. I'm gonna need more room because the concept of choppers is just fascinating. So let's start off by reminding ourselves of the pink noise and the thermal noise bandwidth, right? And I'm going to, of course, have some amplifier, and I'm going to keep this kind of the system block level. So it's going to have some offset voltage in it, right? And when I come in, I'm going to go, okay, well, if I amplify a signal here, I also amplify the offset voltage, right? Well, the offset voltage is way down here, right? And the peak noise, in fact, ends here. There's nothing I can do about thermal noise, right? That it's just kind of a inevitable part of having bandwidth. But if my signal were a high frequency signal, the pink noise doesn't matter, right? But let's say that this is like, I'll use 10 kilohertz just for example, and let's say my signal bandwidth is like 2 kilohertz or something, right? I chose it. This is like a reasonable bandwidth for certain like biological signals. So this is actually really cool in biosignal measurements, okay? So the pink noise goes out to 10 kilohertz. I care about stuff up to 2 kilohertz. So this is not up here. We can make it up here, can't we? How would we do that? Modulation. So let's go ahead and modulate the signal. Okay. So we come in, we modulate it up. Now my signal is sitting somewhere up here, right? Offset is still DC. I come out, I need to make it go back down, right? Because I want the original signal, I want a baseband signal, especially for ADCs, right? Like if I didn't care about the cost of the ADC, I wouldn't even have to modulate this back down. And I could do it all digitally. But let's say that I care about the cost and expense and the power consumption of my ADC as you do in most applications. So let's bring it back down to baseband. And then what happens? So offset is 10 kilo, like, right, 10 kilohertz. It goes up here.
Offset's 10 kilohertz.
Sorry, it goes up to, the peak noise goes up to 10 kilohertz, right? So 0 to 10, it gets modulated, it comes out here, it's still 0 to 10, it gets modulated, say to like 20 kilohertz or something, right? Because this is just a multiplier and it pushes this one back down to basebands, right? So as long as these are modulating, at the same frequency, right? We are multiplying by it just splits it in both directions, right? So there's the negative frequency band that stuff is happening. Well, we push our signal up to like 20 kilohertz. It goes through, that's 20 kilohertz, gets pushed back down to baseband. And I create a low pass filter that gets rid of the now 20 kilohertz level DC signals. Right? Ta-da! There is no DC left. Right? In an ideal world, this would work perfectly. Now, these circuits, right? Anything that's modulation can get kind of complicated, kind of quick, right? It turns out there's this really stupid, easy way to deal with this. And they draw it. I'll just show you the drawing first. Like this. But all this is, so they plug this symbol in for here, and all this is a switches that, I'm going to copy this down because I always make a mistake. One, I'm going to call this I0, I1, so I don't screw this one up. And then I1 up here, and I0. So, which this is a, sorry, where are we going with this one? I1. Oh, I see what I did. Sorry, I'm a really terrible artist, basically. Anyways, this symbol makes more sense to me because basically they take turns. One is I0, I1, B0, out 0, out 1. That's a terrible letter. F, I'll use F. F is a good output that I use all the time in my digital classes, so I'm going to do that. Right. So in phase 1, I0 is connected to F0, and phase 2, I0 is connected to F1, right? It just constant back and forth, which makes square wave modulation, right? I am multiplying it by a square wave. I would like to multiply it by a sine wave, right? That's a better modulation. But it turns out that as long as we don't really care, we care about this fundamental frequency more than we care about any of its harmonics, because it turns out that chopping is not very good for anything beyond tens of kilohertz. It's not a very wide frequency thing. So auto zeroing is very good at wide bandwidth applications because with good choice of architecture, you don't really lose much in the way of bandwidth, if anything. Chopping is not really the same. Partially because of an issue, right? There's nothing that really stops us from switching at a high speed conceptually. But once again, it's this pesky parasitic capacitance that we have left over from our CMOS devices, right? Because if I want this to be a little IC that you can buy and go throw onto a chip, I want this to be as simple as possible, which means CMOS devices, which is why we use the square wave. CMOS devices have parasitic capacitance. They bounce back and forth, and they share just a little bit of charge between each other. And this is really kind of just a conceptual way of doing it. We can go do a whole bunch of math and prove why it works this way. But basically, as they switch, there's just a little bit of lingering charge when they go back and forth between each other. And so they have a little bit of knowledge of what the other one is doing. That's another way of saying there is some resistance between them, basically, right? They have some resistance between both inputs because there's a little bit of current that flows between them. Turns out the faster I go, the more it shares, which means lower resistance, which corresponds to lower input impedance. That's what's happening effectively, is the faster I switch back and forth, the more I reduce my input impedance. So that's kind of where this fundamental limit of how fast can we chop comes from, is eventually I will have such bad input impedance compared to whatever my sensor is that it doesn't work anymore. Also, you have an additional challenge of your duty cycle, right? The percent high, percent low has to be exactly 50%. Because as soon as it starts to bounce back and forth, it gets unequal sharing and you start losing some of these benefits of modulation, right? Because it's not exactly the frequency that you would want it to be. And so let's say we have a really small signal, right? Which is kind of what we like to measure. So say this is like a 10 millivolt input signal. And it's chopping at 50 kilohertz, not very fast. And we're gonna take a very small percent skew, say it's like 1 nanosecond of clock skew. So 1 nanosecond off of 50% duty cycle, you end up with a residual ripple of 1 microvolt for just 1 nanosecond. So it starts to add up kind of fast. And so we kind of need a good, right? It doesn't have to be perfect. 1 microvolt isn't a lot, but 1 nanosecond is also not a lot. So we need to be good enough, which is another reason we like to use CMOS devices, right? Because they react really quickly. We can do them very fast. They're going to be minimum size anyways, so let's use them. They switch back and forth. Aha, we've avoided most of our problems. Yeah. So if we look at this in the frequency domain, just real quick to kind of hammer it home. If I start out here with my signal, right? My low frequency, whatever signal I'm interested in looks like so. And then I call this point V1, okay? So at V1, I've modulated my V in and have not modulated my V offset. So I end up with this. I'm trying to decide if it's better to draw multiple. Shrink this down just a bit. We'll call this at V1. Our signal is now hanging up here with some harmonics, right? It's going to have harmonics anytime, especially because the square wave is not really good. It's actually going to kind of smear him a little bit. And our noise is this, right? Our offset of our amplifier's noise, both its offset and its peak noise are like that. Well, then we come through and we call this point V2. Well, at V2, what happens? Well, we're going to modulate it again, right? Which is going to both push this guy higher and lower so that I end up with signal, my super artistic skills, and the noise, which is here, is now pushed with, harmonics. Okay, that's V2. Then all I have to do is go throw in that low pass filter. And it goes away. So if we go back. And we want to consider like our, right, like I did with the auto zero, and I did the kind of the before and after, what does the spectrum look like? So noise before chopping, if he looks like that, oh, it's going to be my noises as dashes. Okay, that's my noise, right? After chopping. It's going to do something like that, where it actually doesn't affect my thermal noise, and this has no impact. So this is noise before and after chopping, or after. Okay. This is why if you design it right, which my low pass is not quite perfect, right? But if you design it well, your 1/f noise is gone, like completely eliminated, which is awesome. You do have some residual artifacts that happen, because there's this unfortunate thing that happens when you're switching back and forth. That charge sharing that I was talking about actually kind of diminishes the amount of gain that you actually have. So you have the amount of gain that you should have and the amount of gain that you actually have, and they're different. But we have this magic tool as electrical engineers that we can use to fix this. Positive feedback, or sorry, negative feedback, right? We just use negative feedback. We enclose one of these whole systems, the chopping, into negative feedback, and we can actually correct for any of the gain. So you don't have to worry about the fact that the gain isn't ideal, because you can just go chopper, amplifier, chopper, amplifier, this is where things get super nice. So have you guys done, oh, this needs a ground. Have you guys done any multi-stage amplifier design? I know the CEs probably haven't, but have the E's, right? What is one of the big things that we have to do, or we have to worry about when we have more than one stage enclosed in the same feedback? Have you done like multiple stages inside of a closed loop, multiple amplifiers? Have you done that one? So Miller capacitance doesn't mean anything to you guys?
What capacity?
Miller capacitance. You know, maybe.
Sounds familiar.
Okay, that's all right. It's all right. This is like one of those things that is like advanced. I shouldn't say advanced. It's like the first like master's level integrated circuit course. If you're to take it, you kind of get into. Miller capacitance is this thing that we're going to, well, actually talked about it before. I just didn't call it that, which is where we use a capacitor in positive feedback to kind of reduce the issues that we have with stability, right? Because now I have two dominant poles inside of one feedback loop, which plays havoc on our stability, but we can mess with the location of one of these poles. This guy's also going to have a VOS actually that I'm going to put in for a reason. We have what's called a Miller capacitor, which goes into positive feedback, and we can then actually mirror it both across them and add a second Miller capacitor here. This helps both keep it stable, and it turns out it also turns into our low pass filter. So now, instead of having all this complexity that I have to go build for the low pass filter, I built it in while also solving the problems of stability. So you don't need to necessarily know deep about Miller capacitance, but Miller capacitance is something we use to deal with stability of integrated circuits, of multi-stage amplifiers specifically. One other thing, this is the same, right? We're just iterating on the same thing here. The gain of this one, which I'll call AV1, AV2, which one should be bigger? First, AV1, because if this guy's gain is big, it means the offset here doesn't matter, right? Because if I have a 1 millivolt signal that I multiply by 1,000, which is reasonable actually, right? Because that puts it in a volt peak to peak. 1,000 is a fine number. Well, now I have a 1 volt, and let's say that my amplifier itself had 10 millivolts of offset. Well, that would play havoc with a 1 millivolt signal. But 1 millivolt is now a volt, and a volt compared to 10 millivolts of offset is who cares, right? That's just margin of error. Once again, unsurprisingly, charge injection matters, right? And those switches are going to be throwing back and forth. Charge injection is going to throw into here. We're going to get spurious noise. Again, if we're sampling with an ADC, we just don't sample during that time and nothing matters. However, the one thing that does happen is if you go, because this chopping frequency has to be fast, it's not like the auto zero where we can kind of choose, is the charge injection will create a waveform that looks like this. And the faster we chop, the closer these get together, which creates some DC voltage. This is where our residual offset comes from in chopping, is basically the average of those chopper ripples. Once again, it turns out that making these smaller and smaller is really useful because the ripples get smaller. The flip side, smaller devices have higher input impedance or have higher on impedance, right? Because it's smaller, less current can flow, which means I put more noise at the input of my amplifier. These ones are really cool. If you were to like your choppers, you're starting to look at like the 50 nanovolt range pretty comfortably, and people have achieved like 10 nanovolts of offset for like low frequency biosensor applications, like just almost nothing. It's utterly incredible what these can do. There is of course a fundamental lack of bandwidth or loss of bandwidth, right? We're just have to, because we need, these amplifiers have to be fast enough to handle this modulated signal instead of only having to handle the baseband signal, right? So that's one of those issues. Chopper amplifiers are one of those ones that people are scared of because when they were around for the first couple of years, they were really bad and they were like this really good idea that never works. They're now kind of hitting mainstream markets that you can go out and use and reliably know. And there are app notes that are growing in usefulness, and you can go out and use one of these if you have very precise measurements that you need to deal with. I'm going to try and find an excuse to do a lab where I'm going to go buy some of these chopper amplifiers so that you guys can do it, so it doesn't stay just this conceptual thing, right? Because I like to get hands-on for the sensor stuff because it matters, but I'm not sure I'll get a chance to do that, but I'm going to try. One thing that also bears noting is that instead of, I'm just going to draw it again. Instead of this feedback that we have this way, we can use just one amplifier like we did in the initial one. And then after here, we're just gonna add a little summing node where at this point, I drew that too small. This is an integration symbol, not an S. I'm not good at drawing them. Integration. This is an integrator that's just going to look at the output, do the integral, right? It's just slowly adding up over whatever the offset is, which the chopped signal should have an average of nothing, right? So anything that it is integrating is an offset. because the positive things subtract from the negative things when we integrate. That's 0, offset, feed that back around, add it in, and we've actually done an even better job of removing that residual offset. You can also, and I'm not gonna have time, and it doesn't really matter because this is like just from like an actual nerdy engineer design standpoint, people have started combining choppers and auto zeros. So they use chop set for the pink noise and you use an auto zero to extend the bandwidth, and you have this kind of dual path architecture. And so you don't lose very much bandwidth, you remove pink noise and you remove offset, and you have these really cool but very expensive amplifiers. Okay, so that was just a lecture that I wanted to do because I want you guys to be familiar with choppers, because they're one of these things that are new and aren't talked about in undergrad programs or master's programs at most universities yet, because as people still don't understand how cool they are and how useful they are for precision measurements. My goal over the weekend is going to be trying to do the audio amplifier lab, so that I can have you guys do it without worrying that if it's going to work or not. Well, as long as I do at least some part of it and get it up and working, then I'll make sure I'll let you guys go ahead and start that next week. If something crazy happens, I think I have time to do this, but if something crazy happens, then the next lecture, regardless, I think the next lecture, what we do whenever it is going to be the final steps for preparing a signal for an ADC, right? So we've talked about audio signal conditioning, now we've talked about precision conditioning. We can go and talk about how do we prepare a signal to get recorded in an ADC. And I will talk about both D to A's and ADCs, but ADCs more because they're more complicated. But right, ADCs are intrinsically part of any data acquisition system, and any sensor. Most sensor systems are digitized these days, right? Back in the day, they didn't digitize it. They would do largely analog control systems that based off these sensors. But digital technology has gotten so good. Now the main goal of any instrumentation system is to turn it into a digital signal as soon as we can, right? That's like really what we're trying to do as an analog designer if we're doing signal conditioning, which is why we have two different types of engineers that we used to refer to. We used to have analog engineers and digital engineers. And then you started calling in these mixed signal engineers, which I consider myself as, I do ADC design and analog instrumentation design, because analog designers themselves are kind of going away because we're trying to digitize faster. So when we do this analog signal conditioning, it's all to prepare it for an ADC, which it turns out that analog designers are much better equipped to design ADCs than digital designers are, because they're fundamentally analog circuits. Actually, it's just the process of doing that conversion. And so most analog signal designers have started considering themselves mixed signal because it's more marketable, right? Because you kind of need that both. So when you hear the term mixed signal, it typically means doing that conversion, either analog to digital or digital to analog. Analog to digital is harder than digital analog in general. Anyway, so I'll talk about what types of ADCs are. So if you go read a data sheet and it says a SAR ADC, that means something to you, right? And you can then, instead of having to go start looking for ADC, right? If you had to go pick an ADC for an application, like let's say I was told you to go, I need you to measure the signal from the force sensor that we were working with. What specification would you use to go look for an ADC? Resolution, right? That's a pretty good one to use, especially because we don't really care about the frequency. So you're going to go use all those calculations we did, the minimum resolution in the analog world, pick whatever your minimum resolution is to deal with that. But it starts getting more complicated when you start asking things like how fast. So like if you took 3610 from me and we started doing, right, we made, if you didn't, I'll explain real quick. So in my 3610 class, I have them generate a sine wave with a D to A digital analog converter, and they record that signals with an ADC. So that loop back, there's an issue with the ADC where the ADC is actually very slow. It takes a long time to convert, but it's fairly accurate and they're very cheap. And it's because it's what's called a SAR ADC. So next time I'll talk about the types of ADCs so that when you go looking for an ADC that you need more than just what is its resolution, you at least know what to put into the DigiKey search bar to go buy something. Even if you will never design one, it's fine. It's still very beneficial to understand what they're doing and where the ADCs are. They've kind of stagnated anyways in the design world for ADCs. They've been pretty much the same for years. People get their PhDs off of saving like 1% extra power in an ADC architecture. They're like, yes, PhD, because they've been done to death because they're one of the most important parts of any system. And then, yeah, anyways, I'll get there. I'm going to post a simple assignment. We need to do some other homework, kind of, they're a little bit small. And we have been a little bit incentivized through the library system to make you guys use the library. So don't worry, it's going to be basically I'm going to have you in a one half to one page. I'm going to make you guys go look up a paper that is either Chopper or AutoZero for a specific application, and then just write up like, why did they design this amplifier for this application? What benefits do it do? What are they talking about of its benefits compared to other ones? It's going to be pretty simple. You're just going to go look it up, write a little thing, and it's going to help you. Part of the reason I want you to do this is start familiarizing yourself with the IEEE catalog if you haven't used it yet, so that when, especially for the master students, you're going to have to go for the final project, you're going to have to go write a little blurb of kind of background on whatever sensor system you decide to design. So I'm going to start familiarizing you with the IEEE library. Anyways, that's time pretty much. I mean, it's a little early, but I think we're good to go.